I'm Andrew, and I used to host Manchester Skeptics in the pub until, well, you know. But despite everything, it's been lovely to see skeptics groups across the country come together to put on online talks as Skeptics in the Pub online. I mean, legally, of course, we can meet in the pub again, but alas, we believe in science and evidence, so here we are. We follow the same talk format as the old pub meets. We do a talk from an expert speaker, we have a break and then a Q&A, and then we have, new for the online versions, an open pub session in Zoom at the Lock-ins Razor. If you want to ask a question in the Q&A, then head over to sitp.online/ask. And if you can't think of a question, then go there anyway and vote on one of the interesting questions that you'd like to hear the answer to. I'm also going to be posting that link in the chat throughout the event in case you didn't get it, as well as the links to join the Lock-ins Razor, watch previous talks on YouTube, buy some merch, or just throw some money our way if you like what we're doing. Our speaker tonight is Dr. Cass Hall. Cass studied at Sheffield, Edinburgh and Leicester before taking a tenure-track position at Georgia, where she uses supercomputers to study how distant planets form. In January, she won the Winton Award given to postdocs with especially promising careers for her work joining up the theory of protoplanets to the observed data. Now, please post those clap emojis in the chat as I hand over to Dr. Hall.
Hello, everybody. Thank you so much for having me. It's my absolute pleasure to speak to you all today. So today I'm going to be talking about where alien worlds are born, so exoplanets and their formation environment. So just to give you an overview of what we're going to talk about today, I'm going to start with the big questions. So why do we care about planets elsewhere in the universe? Then we're going to talk a little bit about what exoplanets are, what kinds of exoplanets there are, how they are different from our own solar system, and how we detect them as well. Then I'm going to talk a little bit about my research, in particular what I look at and what I'm interested in my day-to-day research. And then we're going to go back to the big questions at the end again. So starting at the beginning, so really I want to talk to you about what it means to search for alien worlds. Now, I don't mean little green men on Mars, although that would be incredibly cool. I mean the real search for exoplanets, planets like our own, and what that means for whether or not there is life out there in the universe. So this image that you can see here is of the Translator Plateau in the Atacama Desert in northern Chile. It is the site of ALMA, and ALMA is a radio telescope. ALMA stands for the Atacama Large Millimeter Submillimeter Array. And this instrument, which is actually an array of these antennas that you can see here, has revealed to us a whole nother level of planet formation. So what I really like about this image is that you can see from it that our night sky is filled with stars. So we've got the Milky Way, which is the center of our galaxy in the top right there of this image. So we're at a point where we can search not only for exoplanets, but also search for exoplanets as they form around their host stars. What's cool about this is that this is, in some sense, equivalent to looking at the formation of our own solar system 4 billion years ago, although it is happening today when we look at these objects. So searching for these planets, we can ask some of the biggest questions that humanity can think of. Like, why are we here? What is the reason that life evolved the way it did? Why are humans the dominant species, for better or for worse? How did Earth form? So Earth is special. Nothing else in our solar system is really like it. So far, we haven't found anything else in the universe that is like it either. What were the conditions that allowed Earth to form? Why do we have so much water? Why is our lithosphere so thin? All of these questions are really important in trying to understand the place of humanity in the universe. How did life begin on Earth? So if we can search for signs of prebiotic chemistry, molecules such as formamide, for example, which are precursors to some of the essential chemicals needed for life, like proteins and amino acids, these may help us to understand how life makes this leap from inert molecules to self-replicating molecules and ultimately to walking, talking human beings who occasionally sometimes do have a brain between their ears. And perhaps the biggest question for me, philosophically, theologically, for society, are we alone in the universe? So this is the first time in the history of humanity that answering this question is within reach. So with the launch of new space missions, such as the James Webb Space Telescope, we may be able to find some answers that help us quantify the probability of there being life in the universe. So this is NGC 6744. It is a spiral galaxy that is very like our own Milky Way. Now, I'm showing you this image since we can't get an image like this of our own galaxy because obviously we exist inside it. But we've been able to make measurements that tell us that our galaxy looks something like this. It is a spiral galaxy. It doesn't look wildly dissimilar. So in every single galaxy, there are hundreds of billions of stars. We know in our own galaxy that there are about 400 billion stars. We also know that there are about 400 billion galaxies in the universe. We also know, statistically speaking, that each star has at least one planet around it. So we know this now. It was something that we didn't know, but we do know it now. Everywhere we look around these stars, there are planets. They are very much the norm. There are planets absolutely everywhere, teeming with them. And we know this from transit surveys. We know this from gravitational microlensing surveys. We know this from radial transit surveys. We know this. So everywhere we look, stars have planets. This means that there are at least 10,000 million planets in the universe. Or, if you prefer scientific notation, 10 to the 23. So considering this, we think, okay, maybe we are rare, but also there are just so many planets in the universe. It begs this question, do you think we are alone? So before we go any further, I want to ask you all, do you think we are alone in the universe? So everyone, take out your phones, your laptops, whatever, and please go to this poll. So don't worry, I'm going to leave the link up in the bottom left of the slide for a little while I'm talking, but I want to know what you think. So sometimes I think with so many planets out there that there must be life. But on the other hand, the existence of life at all is incredibly precarious because life is complex and the conditions that led to life are also incredibly complex as well. Okay, so let's talk a little bit about exoplanets and what actually an exoplanet is. So an exoplanet is a planet in orbit around a star that is not our sun. So one of the most amazing things is that many of these planets aren't anything like the planets that we find in our own solar system. There is no analog for them in our own solar system. Some of them can be much more massive, far larger than Jupiter. So this is a good example here. This is Kepler 13ab, and it is much more massive than Jupiter, which is the largest planet in our solar system. So Jupiter is just 1/1000th of the mass of our central star, our sun. There are hot Jupiters. Again, this is something that there is no analog of in our own solar system. These are objects with incredibly high surface temperatures, some of which can be hotter than the surface of dwarf stars, over 3,500 degrees Kelvin. So their orbital period, the time taken for them to orbit around their central star, is less than 10 days. So you're putting objects that are somewhere between 5 and 10 times the mass of Jupiter, and you are putting them well inside the orbit of Mercury. So these solar systems look very different than our own solar system. Another class of exoplanet for which there is no analog in our own solar system is a super-Earth. A super-Earth is a rocky object that is, much more massive than Earth, but it is less massive than Neptune. They tend to kind of average out at around 17 times the mass of Earth or so. But because it's more massive, the surface gravity is much higher. So what's interesting here is whether or not these objects have an easier time holding on to substantially more atmosphere than things that at Earth mass tend to do. Another interesting thing is that most stars actually form in binaries or higher order multiple systems. So I mean, stars that form together in groups of 2, 3, or 4. Our star is kind of weird in the fact that it is a single star. In fact, most stars don't form like this. The logical question to ask at this point is, can planets form around binary stars, or is the gravity too perturbing for these objects to form? Either can the planets form around one star or around both. And this is really, really interesting because what I'm showing you here is a computer-generated graphic of TOI 1338b. It was discovered by a high school junior named Wolf Cukier in 2019. And these systems are really, really exciting because they are particularly difficult to detect. We don't normally hunt for exoplanets around binary systems. And the reason for this is because we deliberately try to avoid binary stars because the signal is so messy. You basically have to do a lot of very clever data analysis to get rid of all of these effects that comes from searching for planets around binary stars. But we know that planets can form now in binary systems, which makes us hopeful for maybe finding planets around tertiary and higher order multiple systems as well. So how do we find exoplanets? How do we go about actually detecting these objects? Generally speaking, it is very, very difficult to directly image an exoplanet because they are so faint compared to their central star that they orbit. You basically have a contrast challenge. You have to do something to kind of get rid from all the photons from the stellar light often to be able to detect these objects. It does work sometimes. Sometimes we can get direct images of them, but only for the most massive objects. So there are three main ways: transits, radial velocity, and direct imaging. So transit is by far the most popular method. That is how we have found the most exoplanets so far to date. I'm going to talk a little bit about the transit method first. So the transit method is really kind of conceptually, at least, very simple. The exoplanet passes in front of the host star, and what happens is we detect a drop in brightness that is basically proportional to the surface area on the sky of the planet and the star that they occupy. And what's great about this method is that it gives us the size of the planet. The larger the planet, the larger the drop in brightness. So transits also give us the orbit size as well, how far away these planets are from the central object. And we know this because if the transit repeats, we can time how long it takes to repeat. And we know from our gravitational theories, such as Kepler's laws and Newton's laws, the exact relationship between the orbital period and the distance from the star. So this has been the most fruitful way to date, and it's certainly helped us get an awful lot of information about what these exoplanets are like. The only issue with the transit method is that you do not get the mass of the object. But with the radial velocity method, you do get the mass of the object. So with the radial velocity method, what happens is you have a planet that is in orbit around a star. And actually what is happening is that both the star and the planet are in orbit around their common center of mass. Generally speaking, the center of mass will be somewhere inside the star because the star is so massive. So what tends to happen is that this massive planet will slightly make the star wobble a little bit on its axis. So when this happens, if you were to look at the star as this is happening, it's wobbling slightly backwards and forwards along the line of sight. It's actually moving in a circle, okay, but it's wobbling backwards and forwards along the line of sight. Now, light is a wave, just like a sound wave. So if you can imagine when an ambulance is coming towards you and you hear that distinct sort of sound, or any fast-moving vehicle, what's happening is that the sound waves are being compressed as the object moves towards you, and they're being extended as the object moves away. The same thing happens with light. It's called redshift and blueshift. So blueshift when the object is coming towards you, redshift when it's moving away. So what happens is you have a star, and it basically has atomic fingerprints, is what I like to call them. These black lines, these spectral absorption features. And what happens is certain molecules absorb light at certain wavelengths. So we know that, for example, helium or hydrogen or whatever should absorb light at a very specific wavelength. So if that position at which it should move light is slightly changed, you get this wobble that you can see backwards and forwards of this observed wavelength. From this, we're able to infer how fast the star is moving backwards and forwards along the line of sight towards us. And then we're then able to also infer the mass of the exoplanet around it. So the radial velocity method is very useful because it will tell us the mass of the object. But we can also directly detect these exoplanets as well, as long as they are massive enough. So this is a really good example to show you. This is called HR 8799. It's one of my favorite systems. It has these massive planets orbiting it. Each one is about 5 times the mass of Jupiter, so it doesn't look anything like our own solar system. So this was taken with the Keck telescope over many, many nights, and all of these images were basically stuck together to make a sped up movie. So the green line shows the radius of Jupiter's orbit. So just to put into context here, how much further apart these planets are than the planets in our own solar system. It is so, so different. So in this particular system, HR 8799, you have 4 of these objects, and each of them are 5 times more massive than Jupiter, orbiting at 2, 3, 4, and 5 times further away from the sun than Jupiter is. So we can directly detect exoplanets, but only if they're very, very massive, because they tend to be very bright, and also far enough away from the star that we can do lots of clever things to cancel out all the stellar light coming from the center. We can actually make out these images in contrast. Okay. So now I want to talk a little bit, after setting that sort of scene and setting the context, about my research. So this here is a plot of all known exoplanets. We have mass and separation, both in logarithmic scale, with our own solar system plotted on top. So what's really interesting about this is you can tell from this kind of cluster in the top left here that there are a lot of exoplanetary systems that really don't look anything like those that we see on our own solar system. And a really interesting question to ask is, why does this plot look like this? So our solar system certainly seems to contain things that are atypical. Some of it is selection bias, which we are currently, what we are limited by and what we're currently able to identify because of current technological capabilities. Some of it isn't. There are just planets that don't have, or don't seem to have equivalency in our own solar system. So this is a pretty similar plot. It's just showing exoplanets as a function of size and distance from their host star. I really like this plot. It's just a little bit more simple, so you can kind of make out what's going on. So what I like about this is it really gives you a sense of how these objects are different from our own solar system. So you have these hot Jupiters, these very massive objects very close into their central star. You also have these very cold gas giants that are still very massive, but they're much further out. You also have lava worlds and rocky planets and ocean worlds and ice giants. And the really interesting question here is, how do we explain this diversity? Because to me, this is the biggest question that we're trying to answer with all of our research. How do we explain this diversity that we see in the exoplanet distribution? What is it that's driving these differences? So the key to understanding this diversity is that we need to look at where exoplanets form. And this is really difficult to do because when exoplanets are being formed, they are buried in a huge cloud of gas and dust. There are not very many photons. Photons are particles of light that actually manage to escape out of this cloud of gas and dust. So it's really, really difficult to look at these objects while they are actually forming. But it turns out that now we can, and this has only been a very kind of recent development that we've been able to do this. So exoplanets form in objects that look like this. This is a protoplanetary accretion disk. It is shaped a little bit like a CD. It's a very flat object, okay? It is also very, very, very big. So the green line here indicates Neptune's orbit, which is 30 times the distance from the Earth to the Sun. So this image was taken by ALMA, the Atacama Large Millimeter Submillimeter Array, in 2015. The object is called HL Tau, and it was the first example that we have of exoplanets being caught in the act of formation. So each of these dark rings that you can see here, okay, each of these dark rings is a forming exoplanet carving out a path in the dust. We have never seen anything like this before. I cannot emphasize just how young this object is. Our own solar system is about 4 billion years old. Okay, by comparison, this object is a few 100,000 years old. It's orders of magnitude younger. We'd never before seen anything like this because we didn't have the resolution to do it. We can't look at visible wavelengths of light because the dust and the gas basically obscures it. So you have to look at longer wavelengths of light, millimeter and radio, in order to probe down into this object. So for those of us who aren't astronomers, I just want to point out where we are finding these things in the night sky. So this is Taurus. It is a molecular cloud region, and this is where we find HL Tau. So the most dense regions are called molecular cloud cores, and when they are cool enough, they collapse to form stars. And what happens is that angular momentum must be conserved. If you've ever watched an ice skater, spinning very slowly and then all of a sudden taking in their arms to make themselves radially smaller, what happens is that they spin faster. And this happens because angular momentum must be conserved. And this is how accretion disks form. The only object that conserves the only way to conserve angular momentum in an object that is collapsing radially inwards is if it collapses into a disk. It can't just collapse into a straight ball, okay? So this particular star formation region is towards the constellation Taurus. It's basically in between Taurus and the Pleiades. So what's particularly cool here is that this HL Tau object, the system that I just showed you, was actually the first of many. So these planet-forming and planet-containing disks are pretty numerous. As long as we're looking around really young stars, so we're looking in the right place, they're a few 100,000 years old, we are finding them. And this really messed with our understanding of planet formation, because to have these rings, you need planets that are about as massive as Saturn or Jupiter, depending on some of the properties of the accretion disk, in order to carve them out. But in our recently upended paradigm of planet formation, it takes millions of years to form objects this massive. And this begs the question, how do systems that are about 100,000 years old have planets that take 10 million years to form inside it? This is an obvious paradox, right? So the issue is that this is not possible. This paradox is not possible. We need better formation models because our current ones have crucial physics that is missing. So if we want to solve this mystery and we want to get to the bottom of things, then we need formation models, because without these models, okay, without these supercomputing simulations, we're going to have all of this data with no understanding. Astronomical research falls mainly into two fields. You have observational and you have theoretical. Mine is mostly theoretical. Generally speaking, I use supercomputers to try and make simulations of planet-forming systems. And then what I do is I use those simulations to either make predictions about what we're going to find or try and explain things that we've already found. Now, people often ask me, okay, how do you go from, supercomputers to actually getting, movies and images and these sorts of things of these objects out? And basically, we have to solve a bunch of equations that are really, really difficult to solve, and we're lazy, so we make the computer do it for us. So these are what some typical equations of fluid dynamics look like. This is most of what I stare at every day. So I know it looks super confusing, but it's not important. What is important is that these equations are what allow us to create the models of planet formation. So exoplanets form in accretion disks. The birth environment is called a protoplanetary accretion disk. So this is a really interesting example. What I like about this particular object here is that the disk is so massive that it develops spiral waves under its own gravity. So accretion disks are mostly flat disk-like objects where planets accrete both gas and dust, ultimately growing into full-size objects and protoplanets. And what's happening here is this simulation is of a very, very young accretion disk before it has formed any planet. So this is kind of the earliest stages of a disk's lifetime, is when it will be what's called gravitationally unstable, and it develops these beautiful spiral waves that you can see here. So why do we need these simulations at all? Why can't we just make inferences from observational data? And the answer is that there is a very large gap in time between the formation of a solar system and its final planetary configuration. We can't observe these processes, right? Like, humans have not been around for this long. We can't observe a lot of the physics that happens. So what we do instead is we simulate the laws of the universe so that we can make this leap in understanding. So the question is, how do we go from a system like this with a few giant planets on the left while it's forming a few 100,000 years old to a system like ours with the configuration that we do, with rocky planets on the inside, gaseous planets in the middle, and ice giants on the outside? So if we want to understand why there are so many different varieties of exoplanets and why so many of these systems don't look anything like our own, then we need to understand what is going on at the time of their formation. Because it is the processes that happen while the planets are embedded in their disks, shown on the right, that decide how big these planets are and how far away they're going to be from their host stars when we ultimately detect them either through direct imaging, through exoplanet transits, or through the radial velocity method. And of course, ultimately, we want to know what happened that led to the Earth being this special, unique place, the only place in the universe that we know for sure that has life. And to do that, just like in the case of all the other planets that we know about, we need to work out what happened while the Earth was forming. Okay, so I'd like to go back now to the big questions again, just a little bit more. So back to my earlier question. I said there were 10,000 million exoplanets in the universe. Do you think we are alone? So I asked you to vote. So let's have a look at these results. Okay, interesting. So what we have here, just in case you can't make out what my screen is saying, it was 56% of you said, no, there is complex life out there capable of society. 31% of you said, no, there is simple life out there like slime mold. And 9% of you said, no, there is life like animals and plants out there. And 2% said, yes, we are alone in the universe. Interesting. So I have what is considered actually quite a controversial position in our field. I've been chewed out a few times at conferences because I think, on balance, the probabilities indicate that we are totally alone. I certainly don't want it to be true. There are many established scientists who disagree with me. There are many people in my own department who disagree with me. And I am, of course, completely willing to revise my opinion with every new piece of evidence received. So far, I have not found anything compelling that makes me think we're anything other than alone. Despite this, I don't think we should ever stop searching. So this is an argument that I think I am making based on balance of probability. But current absence of evidence does not mean there is evidence of absence. I think it is important to continue the search. So Carl Sagan, Enrico Fermi, Frank Drake, all very well-known science communicators. These people in the 70s reasons that we are in a typical galaxy around a typical star, there's nothing really that special about us. We're not in any special place in the universe, really. So by this logic, the universe then should be teeming with life. So it begs the question, where is everyone? So if there are so many planets and there's nothing really special about us or them, then where are all the other complex civilizations screaming their existence into the void, just like humans have been doing since the invention of radio? Where is everyone? So my answer to this is I tend to follow what's called the rare earth hypothesis. And I say that the requirements for complex life in themselves are incredibly complex and, balanced on these really improbable events and like this chain occurrence of events. So you need to be in the right location in the right kind of galaxy, orbiting the right distance around the right kind of star, with the right arrangement of planets in a continuously stable orbit, with a terrestrial planet of the right size that has a magnetic field and a large moon and a substantial atmosphere, at least one evolutionary trigger for complex life, and be at the right time in evolution. This is not easy. So the right location in the right kind of galaxy. Ours is a spiral galaxy. There are several other types. The galaxy can't be too young. If the galaxy is very young, you would not have enough heavy elements to make life, since all elements heavier than helium are basically fused in stars and nuclear reactions and dispersed throughout the galaxy upon the death of the star. We aren't sure what the upper age limit is for a galaxy to host life. The important thing is that it's not too young and not undergoing tons of supernovas and stellar explosions and lots of gamma radiation and loads of black holes. All of these things are really, really bad for life. We also need to be in the right direction. If we're too close to the center of the galaxy, there's probably going to be too much radiation from the central supermassive object, the black hole. If we're too far away from the center, there's probably not enough carbon. So galaxies are basically far more dense towards the center. So if you have more stars, you'll have more dispersion of carbon in that local area. We are carbon-based life forms. We need it to exist. Also, if we're in the wrong place in the spiral arm, we could perhaps undergo too many interactions with other stars, which could disrupt the orbits of the solar system planets. We need stable orbits for life to develop so that we have stable conditions for geological timescales. Oops, sorry, my computer. Oh, there we are. We also need to orbit the right distance from the star. So if we're too close, we could be stripped of atmosphere almost entirely, just like Mercury, our closest in planet with almost no atmosphere. We could also undergo a runaway greenhouse effect, like what has happened on the surface of Venus if we were too close. There you have surface temperatures around 450 Celsius, which is far too hot to have liquid water. Liquid water, of course, being one of the key ingredients to life. If we're too far out, it is too cold to have liquid water on the surface. From Earth's point of view, at least, this seems to be very important to life, so it is a criteria. We also need to be orbiting the right kind of star. So our star, in the grand scheme of things, is pretty boring. It doesn't have a huge amount of magnetically active flaring activities. We have a few, of course, and they tend to knock out communications every now and again when it happens, but overall it's pretty boring and it's pretty stable. But a lot of other stars aren't like this, particularly dwarf stars. If you have the dwarf stars, basically stars much smaller than our sun, are far more numerous in the galaxy, but these things tend to be more magnetically active. This magnetic activity is not great for life because basically huge amounts of ionized particles end up streaming towards the Earth. They're hugely energetic and can pick away at our atmosphere, depleting the Earth of the protection that we have from all of the radiation that is present in outer space. But we also need the right arrangement of planets. So the Earth has benefited from having two very large planets, Jupiter and Saturn. And what they do is they basically attract most of the asteroids that pass through the solar system. So these asteroids are either steered off course or crash harmlessly, well, harmless for us, into the upper atmosphere of these planets. So this, of course, plays a role in securing the future of life on Earth. It's an awful lot of stuff that may have otherwise passed near us, kind of evades us. This is good news for life on Earth, right? We know that mass extinction events have happened because of objects from within our solar system crashing in and just spelling out very bad news for life. But we also need to have a continuously stable orbit for geological timescales. So we have had a stable orbit for very long timescales, and we're able to work this out from our fossil records in order to gather information about temperature. That is, of course, until humans started pumping huge amounts of greenhouse gases into the atmosphere to cause climate change, but I'm not here to talk about climate change. So requiring a stable orbit may mean we can't have a system that has these hot Jupiters in there. So remember, there are massive planets that may be many times the mass of Jupiter orbiting inside the orbit of Mercury. But what's interesting about these objects is we are pretty sure that hot Jupiters actually form much further out in the disk because there isn't enough building material that close to the central star. So basically, being that close to the central star during formation, they are subject to extreme heat and bursts of intense energy that strips the gas away and would prevent them from forming such massive objects. We also know from simulations that these things, if they form further out, where there is enough mass for them to do so, are able to migrate inwards. In fact, we find that it's almost unavoidable. These things, if they form further out, will basically migrate inwards because the gas of the accretion disk exerts a torque. A torque is basically just a rate of change of angular momentum. If you have a rate of change of angular momentum, then the object is going to spiral inwards. So this massive object slowly meandering its way inwards from the outer regions of the solar system to the inner region of the solar system, what's going to happen is it's going to cross orbit paths with smaller objects. Smaller planets in the orbit will be disrupted. If this is also bad news for life, if something that is suddenly twice as far as has its orbit disrupted and is suddenly twice as far from the sun as it was before, then you're not going to have this kind of precarious balance that we already have in our atmosphere that allows us to have the kind of temperatures that we do. Something is going to change until the object reaches a new equilibrium temperature. We need a stable orbit for life to develop because we know, generally speaking, that wildly varying temperatures are not conducive, at the very least, to complex life. We do have some extremophiles that are able to live either in the upper edge of Earth's atmosphere or around hydrothermal vents as well, but they're not conducive to complex life capable of society. So we also need to have a terrestrial planet of the right size. So this means that the escape velocity, the speed required for a molecule of atmosphere to escape, is related to the mass and the radius of the planet. If a planet is more massive, the escape velocity becomes higher, which means it is harder for gas to escape. If it is harder for gas to escape, maybe we could end up with an atmosphere that is too dense and the planet becomes too hot and it ends up undergoing a runaway greenhouse effect. If the planet, on the other hand, is not massive enough, it is very easy for most of the atmosphere to escape. A thin atmosphere means a lot of the heat can escape, and you basically end up with this runaway icehouse effect. In both cases, we will not be very likely to have liquid water on the surface of these planets, both of which are required for life. Now, a magnetic field is also really important. So the reason we have a magnetic field is because we have a solid metallic inner core and a liquid outer core. So the liquid outer core is mostly comprised of iron and nickel, which we know from seismic waves and analysis of our magnetic field. So iron and nickel are conducting material. They have free electrons basically running around in the surface. So if you get this liquid layer moving, then basically what you have is you have a moving charge. If you have any moving charge, you induce a magnetic field. The magnetic field protects us from ionized particles that the sun spits out, because ionized particles themselves have an electric charge, therefore they have a magnetic charge. It basically protects the upper layers of our atmosphere from being stripped away from the sun's ionizing radiation. Without it, the Earth would be bombarded with ionizing radiation. It would strip away the upper levels of our atmosphere, and then all of the atmosphere that protects us from very harmful ultraviolet wavelengths would just be allowed to penetrate through. This is very harmful for life. Okay, we know the effect that UV has on our skin, on DNA, all of these things. It's very bad news for life. But we also need to have a large moon. So our moon is actually pretty unusual. As a fraction of the size of the planets that it orbits, it's pretty large. It's about 1% of the Earth's mass. So most other moons, especially when we look elsewhere in our solar system, are around kind of 100th or 1000th of a percent. They're far, far smaller. So the fact that it is so massive does a few things. At first, it basically gives us some extra protection from impactors. Any three-body system in gravitational dynamics is inherently chaotic, and it makes it much more likely that an impactor, which in this case would be the least massive object, will be thrown out of our little system and not hit Earth. But the large moon also gives us tides, twice as large as the tidal interaction that we get from the sun. So tides go in and tides go out. We think that this may have played a role in basically helping life move from the ocean onto land, basically through tidal pools, and it allows complex life and speciation and these sorts of things to go on and develop. It's not, of course, clear. This is kind of a hypothesis at the moment, but we know for sure that the moon does basically protect us from impactors coming through our solar system. We also need a substantial atmosphere. So everything that is living on Earth respires in some way, and humans, we know it is breathing. But the atmosphere also protects us from this damaging radiation, such as that from UV light. So ozone, the tertiary form of molecular oxygen, does a really great job at absorbing UV light and therefore protecting us. But the issue is that ozone is not very stable. It is photodissociated pretty easily by UV light. And what that means is when a photon of UV light hits ozone, this tertiary oxygen molecule, basically it breaks up the bonds into single molecular oxygen. It's kind of okay because what happens is this single molecular oxygen will then go and find the double oxygen and basically join up again and form some more ozone. So it's kind of fine so long as it's only the UV light from the outside kind of doing this. If we're also depleting it through CFCs and so on, then of course this process becomes imbalanced. But what's really interesting is that if we find any evidence for ozone around another exoplanet, and we're getting to the point now where we're actually able to detect what exoplanet atmospheres are made up of, that would tell us that there is something really interesting going on and a really interesting chemical process that could potentially be biological in origin. But in any case, you need lots of oxygen to get any ozone because it is so continuously depleted. So you need a pretty thick atmosphere if you're going to keep hold of stuff that is able to actually block out this UV radiation. And there also seems to be a requirement that there is some kind of evolutionary trigger for complex life. So the earliest life we have records for are called stromatolites. They are very early life forms that are basically layers of photosynthesizing cyanobacteria. So the Earth is about 4 billion years old. The fossil record tells us that the earliest life we have records for, these stromatolites, occurred pretty much soon as the Earth was cool enough to be able to house life. So about 3.5 billion years ago, or just over 500 million years after the Earth's formation. What is interesting here is, does that mean that prokaryotic life, so prokaryotes are life forms without membrane-bound organelles, are kind of easy to get going because they happen so quickly after the Earth formed, and basically as soon as it was cool enough to house life, it did. But then what happens was it took another 2 billion years for eukaryotic life forms to form. So eukaryotic life forms are life forms with membrane-bound organelles, and these cells are much more efficient. Because you can have these separate organelles, you can have them doing separate tasks, it makes it more energy efficient, basically because you have things that specialize rather than needing to have non-specialized tasks doing a bunch of different things. So the question there is, maybe prokaryotes are easy to get going, but eukaryotes are more difficult. Now, all life on Earth is descended from what is known as the last universal common ancestor, or LUCA. So this is not the first life on Earth, but rather the last cellular ancestor that we all commonly share. So all life on Earth basically works in the same way on a chemical level. You can have kind of some differences, but it's ultimately all based on the same sugars, the same amino acids, and the same proteins. And we know all life on Earth kind of works in the same way, basically because of this property called chirality. So we have left-handed sugars we have left-handed and right-handed molecules, both sugars and amino acids. But life can only take left-handed sugars and right-handed amino acids. So even though they're found equally as often in nature. So this tells us that all life on Earth is kind of, certainly very strong evidence towards that all life on Earth is related to this last universal common ancestor. So what this suggests is that if all life on Earth is related to this last universal common ancestor, maybe life is pretty difficult to get going because it tells us, well, what if there's only one event in the last 4 billion years in which life can then go on and develop, even though we don't think LUCA was the first life, but it's kind of the mother of all life on Earth. And this only happened once in our 4 billion years history on Earth. Okay, and finally, we also need to be in the right time in evolution. So if we want to detect life elsewhere in the universe, ultimately it needs to be communicating. So if we think about, how long life, and complex life certainly, has been present on Earth, we have been on the Earth and communicating for such a tiny, tiny, tiny fraction of this period of time. Humans are weird. We have complex language. We discovered mathematics. We have hands with opposable thumbs, allowing us to build, create, share knowledge, destroy each other, of course. But even if an animal such as a dog had the same intelligence as a human, they could probably do very little with it because of, a lack of opposable thumbs, right? Sometimes I'm very glad that my cats don't have opposable thumbs, actually, because I think otherwise they would plot my demise. So, of course, our best chance of detecting life out there in the universe is by detecting someone who has broadcast their existence. So alternatively, it would be us, reaching out, trying to find somebody else's radio broadcast. So radio is just light. It is very long wavelength light, but it is just light. So it travels at the speed of light. So here is an artist's impression of what our galaxy looks like. Okay, So we know that we live in a spiral galaxy. Of course, this is just an artist's impression. So the blue dot that you can see here is 200 light years in diameter. So we have been broadcasting radio for about 100 years. So the radius of our signal is 100 light years across. That's it. Okay. The diameter of the Milky Way is about 100,000 light years. Okay. You know, modern humans have been around for a comparable length of time. So to have reached everybody else in our galaxy through our radio broadcasts, we would have been having to broadcast from the moment we appeared in our modern form, which we obviously have not done. So what if other life out there is kind of also in a similar situation to us, right? What if they had empires and civilizations that rose and died and emitted radio and stopped because they moved on to another form of communication that was much more efficient, and we're just going to, you know, not have the technology to receive it yet? Maybe we were like passing ships in the night, right? We weren't the first intelligent species in our galaxy, but they've already died out. We have to both exist at the same time. This is another problem. Okay. So I want to ask the question again. Now that I've gone through this, what do you think now? Has your opinion changed? Do you still think we are alone in the universe? Yes or no? Okay. So don't worry. I'm going to leave the link up in the bottom left of the screen so that you can see it. So what I like to tell people is that these numbers all seem improbably small, but then again, there are 10,000 million planets in the universe. So maybe someone is out there after all. Okay. So just to give you a summary of what we've talked about, studying exoplanets and how they form may help answer some of humanity's biggest and most fundamental questions. We mostly detect exoplanets via indirect methods, such as transits and radial velocities, but sometimes we've been able to directly image them as well, as long as they're sufficiently massive and far enough away from their host star in order to do so. My research has mostly focused on the earlier stages of planet formation, looking at the conditions of formation, actually from the protoplanetary disk and its effect that it has on the ultimate exoplanet architecture of this distance from the central star and the mass of the object. And really, I have no idea if we are alone in the universe, and it keeps me up at night. I hope that we would maybe discover, some life form in my lifetime, but I just think it's really, unlikely. I don't know. Maybe I'm wrong. I hope I'm wrong. I always hope I'm wrong. Okay, so I'd like to go on to the poll results, but I'm just a bit worried that I haven't quite given you enough time to vote. So I'm just going to give you another couple of minutes another 30 seconds or so to vote. Make sure that everybody's had a chance. Okay. Okay, so at the start of the talk, just to remind you, I asked, do you think we are alone in the universe? And this is what the results were, okay? 55% of you said no, there is complex life out there capable of society. 31% of you said no, there is simple life out there like slime mold. 11% of you said no, there is life like animals and plants out there. And 2.2% of you said yes, there is life. Yes, we are alone in the universe. So interesting. Okay, so some people have maybe kind of slightly changed their minds, but not too much. Okay. Interesting. Okay. Thank you very much.
All right. Thank you, Cass. That was really interesting. It's great to see such big topics explained so accessibly. We're going to take a slight break now for about 15 minutes. I think we're going to come back at about 8. Mm-hmm. So, yeah, I will see you all then. Have a good evening. Okay, welcome back, everybody, to Skeptics in the Pub Online. We're here with Cass Hall, and we're going to go through some of the questions that you guys have asked in the interval. And we're going to start with a novel Skeptics in the Pub tradition. Can we see your cats?
Yes, let me just get him out of his box. 1 second. Atlas, come. Yes. Oh, good boy. Oh, good boy.
This gorgeous cat. Is he named after the God Atlas or the Experiment Atlas?
I managed not to lose any fingers, so that was good.
As a result. Is the cat named after the God Atlas or the Experiment Atlas or something else?
The God Atlas. Yeah, I like Greek mythology.
I think everybody does. Okay, so the first question about the actual topic at hand comes from Hall or Picticule, who asks questions quite often at these things. Are we in danger of being too solar-centric in our extrapolation of conditions elsewhere? Could it be that intelligent life exists quite unlike anything that we see here?
Yeah, absolutely. The issue is that we can only go off what we know. We only know of one way that life can exist. So when we're trying to, quantify the probability of there being life elsewhere, you have to make that inherent assumption of, okay, this is what we know life can be like. So something that's really interesting, or that I like to think of, is the reason life is carbon based is because carbon basically has these, you can have like 4 available connections basically to build more complex carbon chains, like carbohydrates and things like that. Another molecule that this could work with would be silicon. Another element, sorry, that could work this would be silicon. The issue with silicon, it has 4 available bonds, just like carbon does, but the energy required to break the bonds is much lower. So what that means is, for example, proteins for life on Earth kind of tend to denature, so they lose their structure at around 65 degrees Celsius. I think it's between 65 and 72, depending on what the protein is. So that's pretty high temperature kind of threshold, really. Silicon, it's much lower. You start to break these bonds at around, I think it's around like 20 Celsius, maybe even lower. So an interesting idea might be maybe life could be silicon based, but because you need very little energy to actually destroy these bonds, the chance of it being, complex life is maybe a little bit smaller. But maybe this could be a way that life could exist. So absolutely, we've been very solar centric, but the reason for that is because there's only one way that we know life exists. If we're making, hypotheses about maybe life exists in another way, we don't have any evidence for that. We know life can exist the way it does on Earth in these carbon-based life forms. So we have to think about it in this way. We can certainly make, conjectures and have ideas and have discussions and try and write down some calculations about what those criteria would be. But yeah, it's a fair criticism, but also I think it's unavoidable.
If there was this kind of to use a slightly tautologist term, alien life out there, what are the odds that it's there, but we just wouldn't recognize it?
The odds are pretty good, maybe. So one of the things that we're able to do now is we're able to kind of look at what the atmosphere of exoplanets are made up of. So not only can we detect them, we can actually kind of tell what's in them. One of the things that we would look for example, would be features like ozone. So ozone is, as I talked about, it's very reactive. So if you detect ozone at all, it's because there's something that's going on that's replenishing it. That could be a signature of, either biotic chemistry or abiotic chemistry. Another would be, for example, chlorophyll. We would look for chlorophyll. So what happens is it's very good at absorbing long wavelengths of light. So when you look at a spectra, which is basically a function of the intensity of light as a function of wavelength, when you look at the spectra basically coming off plants that have been reflected, you have like a big chunk that's missing because they've absorbed it for photosynthesis. So if you see a pattern that looks like that on an exoplanet, then that would tell you that was covered in plant life, for example. I've forgotten what the question was. I was enjoying talking too much. What was the question?
It was about alien life, which is very
yes,
alien.
yeah, and we just wouldn't recognize it exactly because we're looking for signatures like our own. We're looking for things like photosynthesis, biotic chemistry in the way that we would recognize it. There's a chance we wouldn't recognize it. Absolutely.
So the next question on the list is, do you think life in the universe has ever existed? And this has come from Mike L.
It's hard to say because we just don't have any evidence. There's what I want to be true. And what I want to be true is that the universe has been teeming with life, is teeming with life, and always will be teeming with life. And what I know to be true and what I have evidence of is that there is only us. I think it doesn't really matter what I believe, that we have to go on what we have evidence for or what I hope. I don't believe that there's life out there because I have no evidence of it. I hope there is, but that's not the same thing as knowing or even necessarily believing.
Yeah, definitely. So Igor asks, kind of playing into everything we've discussed so far, what's the weirdest cosmic object out there that might have life on it?
So this is a really good question because inherently it can't be too weird. It can't be too different from Earth in many respects if it's going to support life. So I ended up talking about how Jupiter basically has many moons, but it has 4 particularly large moons called Galilean moons because they were discovered by Galileo. And one of them, Europa, has a subsurface ocean. So it has this subsurface ocean because of tidal interaction. So even though it's very, very far away from our sun, so it's 5.2 times the distance between the Earth and the sun. So that distance is pretty far, so it ordinarily would be pretty cold. But if you can imagine bending a paperclip, so if you bend it repeatedly, eventually the paperclip snaps. And when it does so, the point at which it snaps is very, very warm. And it's basically because you've been putting this kind of movement energy, actually turning it into thermal energy. So gravitational tides do the same thing. So Jupiter is a very massive object. And as the planet is in orbit around Jupiter, what happens is the moon is in orbit around Jupiter. And what happens is the moon experiences different forces at different points on the body. The reason for this is that the gravitational force drops off as 1 over the square root of the distance between the two. So what happens then, if you can imagine that this is Jupiter and this is the moon, what happens is the near side experiences a much larger gravitational force than the far side. So what happens is that the object basically stretches. So on Europa, it's very, very icy. So what's happening is as the object is becoming stretched, it's becoming heated. And basically the ice on the lowest parts of beneath the surface have melted and it's become a subsurface ocean. I've been able to take measurements that confirm that this is the case. So this is a really ideal testing ground to see if life could also exist somewhere else in the solar system, if it doesn't just have to be on Earth. We know the biggest and probably the most important constituent for life is liquid water. And we know that there is liquid water on this moon. So one of the things that we would hope to do in the future is to actually send somewhere to probe there and drill down into the ocean and actually take samples. But this is kind of, we'd have to be incredibly careful not to ruin this perfectly pristine laboratory for extraterrestrial life out there, right? Like how you have to be so careful not to bring contaminants. Even if you did build the instrument in a sterile lab on Earth, of course, when it passed through the atmosphere, maybe things could hitch a ride, for example. And we'd have to be very careful in confirming that these things were actually, found on this moon and not found on the Earth. I don't know if it's the weirdest object, but I'd certainly say it would be the best bet for searching for life within our own solar system that doesn't have origins on Earth.
It's always a tricky one, isn't it? What's the least likely thing that's still likely?
Yes, exactly.
Okay, the next question has come in from Picticule again. And he asks, were you surprised at the relatively small shift in the poll results? And how does that compare with other times you've done the same poll with a similar talk?
No, I wasn't surprised. One of the things that I have learned is that if you confront human beings with evidence that contradicts their opinion, they double down and they hold on and they don't change their mind. And that is true of all of us, me as well. So no, I wasn't surprised. This fits in line with everything I know about human behavior.
That is an interesting thing to know about the Skeptics audience specifically.
But it's true of everybody. We're not.
Yeah, we're still humans.
Even if we're scientists, even if we're skeptical, we all do it. The psychology studies tell us that this is the case, and there's nothing special about us, despite, if we like to think that maybe we're more rational. Maybe what we're holding on to is more rational, but with something like this, there's not much evidence, so it's an opinion.
Yeah. Okay, I mean, the next question has come from a big man cow who shall remain otherwise anonymous, who asks, is the chance of anything coming from Mars really 1,000,000 to 1?
I would say it's less than 1,000,000 to 1. We don't really have any evidence for any life on Mars at all. We sent samplers there in the 80s. I think famously what caused some controversy was that there was one experiment that came back inconclusive. But I think basically it was just looking for, reduction reactions in the surface of the soil. I'd say it was less than 1 in 1,000,000. We've looked, we haven't found anything.
Yeah, I feel like life on Mars is one of those things like nuclear fusion. Every so often there's been a news report saying, it's right around the corner. Any day now we're going to discover. It never seems to have happened. I can't remember what happened to any of these.
I think with nuclear fusion, I'm far more optimistic about achieving sustainable nuclear fusion on Earth than I am about finding life on Mars.
suppose that has at least happened once in our solar system.
Yes, yeah.
The next questions come from Dev J, who asks, which is better, Mars, Galaxy, or Milky Way?
Oh, Galaxy.
I feel like any one of those would have been a controversial choice. So let's just move on and let the Twitch chat do its thing. The next question has come from Anonymous and is a bit more back on topic. Could dark matter be a consideration when accretion disks are forming into planets?
Good question. No, probably not. The reason being for this is that so dark matter makes up a good chunk of matter when we think of things on terms of okay, so for context, we have ordinary baryonic matter that interacts with light the way that we know it to do so. Dark matter is just called dark matter because it interacts through the gravitational force, but it doesn't interact through the electromagnetic force, so it doesn't emit or kind of absorb light in any way, shape, or form. On the kind of scales that we talk about when we're talking about planet formation, that interaction is only between baryonic matter. You know, dark matter is so kind of diffuse on these scales that it doesn't really come into effect at all. You know, it matters on galactic scales. Obviously, the original kind of discovery of dark matter was the fact that the rotation curve didn't match up to the baryonic matter that we saw, basically because it was spinning far faster than it should do for the amount of mass that we were able to measure from the light. But that's on galactic scales, which are very, very different to looking around local stars.
Yeah, I think that all made sense to me. It's so difficult to get your head around things on these scales, isn't it?
Yes, yeah. The scales are mind-boggling, I think.
Yeah. The next question is another anonymous one. Is it possible to detect water on exoplanets?
Yes, it is. So we have there's basically a technique called transit spectroscopy, and what happens is when a planet passes in front of its star, you basically have a combined light profile from the star and the planet, and then you also have the light profile from the star only. And when you do this, you're basically able to subtract one from the other, because what happens is as the starlight passes through the atmosphere of the planet, remember when we talked about the spectral fingerprints where you could actually see what a star is made up of? It's kind of the same with a planet. And you can actually see what the atmosphere contains because the light basically absorbs this information on the way past. So you can see whether or not it contains, you know, things like water or maybe, you know, more often it's things like helium in massive planets, for example. So yes, and actually we made a 1 sigma detection of water vapor in the upper atmosphere of an exoplanet using this transit spectroscopy. It's controversial. It's controversial because it's a 1 sigma detection. So a 1 sigma detection, if I remember my statistics correctly, it is a 66.97 chance that it is not from just random statistics. It's not random statistical noise. But to be kind of really sure about things in astronomy, we like things to be at least 3 sigma, preferably 5 sigma. 5 sigma would be, you know, it's kind of a very low probability of this being due to statistical noise. 1 sigma is kind of, it's a weak signal. It was still pretty exciting and it was certainly promising. But I think we need more follow-up observations or at least to find another example of it to be certain. But yes, it's certainly possible and it's certainly encouraging as well. And we have the technology to do that now. Yeah.
It sounds like we haven't seen very many of them yet.
Yes, and part of the reason is that we favour the where we look. There's like selection bias because it's for radial velocity searches. It's easier to look for very massive objects very close into the central star. For transits, you want to look at very large planets as well, but radially large because then they cause like a bigger light drop. So what happens with transits is you basically get like things like stellar fluctuations. A sun is not perfectly uniform in light over time. So what you want is you want a nice strong signal. So if you're looking for things that are smaller and smaller and smaller, so the Earth is pretty tiny compared to Jupiter, it becomes, you know, a very, very small signal that you're searching for, and it makes things pretty messy and pretty complicated.
Yeah, I enjoyed, if I remember my statistics correctly, and then immediately 2 decimal places on the percentage.
Yes, yeah.
That's very impressive. Okay, the next question comes from Feugl, who asks, what do you think of the idea that there's life on Earth with a completely different earthly origin, and we just haven't found it yet?
So that's a great question. But I think it's pretty unlikely, given that. So the reason that we one of the main arguments about life on Earth having the same origin is because of the way our biochemistry works. So there's a huge amount of variance in biochemistry. For example, there's chemolithotropes that basically at the bottom of the ocean eat rock basically and convert rock into chemical energy and are able to get the ATP for movement and all the rest of it, and to be able to actually move around. That works very differently to us, but they still have, everything is still built on right-handed sugars and left-handed amino acids, even though chirality wise and probability wise, left-handed and right-handed stuff are found pretty 50-50 in nature. If we even found one example of life working in that way, where it used the opposite chirality of the molecules, I'd be convinced that there was kind of this shadow life that's present on Earth that's evolved in this other way. We've never found it to date. So I think it just seems pretty unlikely. Where else would it be hiding at this stage? We've been able to go down to the bottom of the ocean through the trenches and our submersibles. We've been able to look at, hydrothermal vents. We've been able to take samples from inside volcanoes. We've looked at tardigrades. We've looked at all sorts of extremophiles and never found anything that worked any other way.
It's a bit of a change of pace for a skeptics talk to be able to say to so many questions, well, we haven't seen it yet, but maybe. Because usually our thing is saying, well, look, there's no evidence that alternative medicine X works or whatever. Mm-hmm. If it worked, we'd have seen it by now. Mm-hmm. And in this, we just get to say, yeah, we don't know. Yep. Maybe. Haven't found it.
For me, it's, people, you're asking me to say, is this possible? And it's kind of like, well, I mean, if something comes along, fresh evidence that changes that, of course it's possible. To date, we haven't found it yet. To me, that means it's highly improbable and probably not the case. But on balance of possibility, no, I don't think it's probable. Is it possible statistically? Maybe.
Mm-hmm. And the size of the universe just means that even if life is out there, we probably wouldn't have found it.
Exactly. So. It's. For example, like we've kind of almost gone radio quiet, right? In the last however many years, we're broadcasting radio less. We're doing it through cables underground. We're making far less noise than we used to. So that means that, okay, we were dead loud and noisy for 100 years. And then those waves are just going to go across the galaxy and passing ships in the night. If there's another species on the other side of the galaxy that is also emitting, but they've gone the same way we have and now they communicate a different way, we're never going to hear those radio signals.
Okay, let's move on to the next question, which is from Pontus, which is, you say a lot of solar systems don't look like ours, but to what extent could that be an artifact of what we're able to detect and see?
Yeah, 100%. So we definitely have not so much confirmation bias, but detection bias. We have detection bias because we are limited by the sensitivity that we're able to do. So, for example, for radial velocity searches, we're kind of fundamentally limited to, signal to within about a meter per second. And the reason that we're fundamentally limited is because stellar surfaces fluctuate at about that level at about a meter per second. So there's nothing you can do about that to get away from that. So if you're looking for something that is causing these variations on less than a meter per second, you can't find it because the star fluctuates and just washes out that sort of signal. So there's also something called the detection frontier. So the detection frontier is basically, the smallest mass at the furthest distance that we're able to detect.
This is the bottom right corner of the graph you showed in
Yes,
slides.
Yes, exactly. Yes, the bottom right corner of the graph. So as our technology improves, we'll be able to push that boundary of the detection frontier. So that is definitely true. But what we're also finding is that, there just are things that don't look anything like our own solar system, right? We don't have hot Jupiters. We don't have things that are 10 times the mass of Jupiter on Mercury's orbit. We just don't have that. And we do find a lot of those. So whether it's the case of, certainly it's true that the majority of things that we find don't look like our own solar system. That's a bit uncertain because of this detection bias. But what is certain is there are definitely lots of things that don't look like our solar system. We are not typical just by virtue of how different everything kind of looks so far.
Are there any theoretical models that say what we should expect to find?
Yeah, so we do this thing called population synthesis. So what that is you basically take analytical equations of protoplanetary accretion disks, and what you do is you say, okay, dust should grow at this rate. A planet, for very small mass objects to ultimately form something like the Earth. And then you would say, okay, very large things would form maybe more directly from gravitational collapse. You evolve these things on, millions of years on a supercomputer, and then you perform hundreds of thousands of these statistical models with basically different random number seeds. And what happens is that generates a synthetic population, and that gives you a distribution of what you expect these exoplanets to look like. And what's interesting is that, here is where we have some confirmation bias, because what we expect is that our population synthesis models are going to look like what we detect. And if they don't look like what we detect, we chuck them out. But the problem is that our detection methods already have these, these biases in, right, from our frontier. So we have to, it's constant. It changes with the data that we get. We have to update our models and vice versa, and it feeds into them.
Yeah, it's one of those fields where you can't run an experiment ever.
Yeah, you can't fit it in a lab, right? So
yeah.
Yeah.
The next question has come from Don or Steelwolf, who asks, what are the best and worst examples of planetary colonization, specifically a show like Battlestar Galactica compared to, say, Star Trek or The Expanse?
I'm sorry, I'm a massive nerd, but not a telly nerd, I'm afraid. I can't answer your question, having never really watched much of either of those programs. I'm sorry.
Yeah, well, I'm sure lots of people in the chat have got opinions which they are now posting.
Yes,
so
yes.
I'm sure we'll get an answer soon enough. Okay, let's go on to the next one, which is from Igor, who asks, are new planets still being formed? Is the rate of their formation on decline?
Yes, new planets are still being formed. So if you remember the kind of reddy orange accretion disk that I showed you, that's a new planetary system that is being formed right now. So our kind of local solar neighborhood, I guess, where we have like lots of stars and stuff nearby, these things are kind of pretty set. They've been around for like billions of years. But if we're looking, towards the Taurus molecular cloud, we're seeing active star formation now. So there's lots of regions that, not too far away, the kind of, a few hundred light years or whatever, where there is active star formation happening now. The star formation rate in the galaxy is the same as the planet formation rate, because stars and planets form at the same time. A common misconception is people think that stars form first and then they form planets, and that's not true. They form together, they form at the same time. Not really on decline in any kind of meaningful way. The star formation rate is pretty constant for a very long time in galaxies, so it certainly hasn't declined in any meaningful way on human timescales. No.
Are we seeing different kinds of stars and planets as the universe evolves and presumably fills with heavier elements? And are they more or less likely to have life on?
Yeah, that's good. So there's basically there's this thing called population 1 stars. So population 1 stars were the first stars in the universe that would have been entirely made out of hydrogen and helium. So stars are mostly hydrogen and helium, but they do also contain heavier elements like carbon, oxygen, nitrogen, etc. Before they are formed through continued fusion, because basically what happens when you run out of hydrogen and helium, you start fusing heavier and heavier elements. And these population 1 stars would have been very, very different. Whether or not you could have formed planets, generally speaking, we think we need dust particles like carbon and silicates to form planets. So I don't know, and we don't have population 1 stars anymore, so that's not a question we could answer. One question that we kind of do know is that we have these things called like kind of rogue planets. So they're planets that have no host star, that are just like drifting through the galaxy. So one of the things that we think happen, it's argued about whether they form directly and they're basically failed stars that are formed by themselves, or whether or not they formed through a star basically coming in on a close encounter, disrupting the orbit and just chucking this planet across the galaxy with no host star anymore. So there is a few different things there. Yeah.
I assume we're never going to find life on a rock planet.
I think it would be very unlikely, right? Because all life on Earth is basically, we all need energy to function, and our energy comes from the sun. The sunlight, into plants and so on and so forth. basically all life functions on sunlight. So if you don't have some form of energy source, because life basically, it's basically just out of equilibrium with its environment. It's complex. It's either warmer or cooler than the external environment. Always it's out of equilibrium. But if you don't have that energy source to keep it out of equilibrium, to maintain this homeostasis in whatever way, shape, or form, I don't see how you could support life.
Okay, let's move on to Dev the drummer's question. Now our understanding's a little more sophisticated. Are there any new and exciting methods to detect exoplanets coming along?
Yes. So my favorite is there is a new method. So basically what happens is while an exoplanet is forming, it carves out this ring and this gas and the dust, just like the orange disk that I showed you. And what's really interesting is that you can basically look at what's called a velocity channel. So if you take, for example, carbon monoxide should emit light at 1.2 millimeters. So as the accretion disk is spinning, what's happening is, that this light, this signature of light, this carbon monoxide, should be emitting at 1.2 millimeters. If that wavelength changes because it's going towards you or away from you, so it's spinning around, which means it has a component along the radial line of sight and along this line of sight as well, you're able to actually tell what the velocity is in that local vicinity because it should emit at 1.2 millimeters. So if it's not, it's because it's moving. And when it does this, you can actually basically pin a model where that planet should be, even if you can't see it in that ringed image that I show you. So if you're just looking at the carbon monoxide emission, this gas that is really prevalent in these systems, you will actually be able to detect forming planets that are otherwise invisible. And that's pretty cool.
That is cool. Okay. Andy Wilson asks, first of all, Andy says, amazing talk and images.
Oh, thank you.
And thanks you. And then asks, how have the exoplanets discovered so far changed physics? Does the Drake equation need to change because we have new numbers? And I mean, I'm not sure if the Drake equation is physics really, but...
So the Drake equation, just for anybody who doesn't know, it's basically a way to kind of quantify the number of intelligent civilizations that exist in a galaxy. I forget what the exact numbers are, but it's something like, the number of stars that could potentially host planets, that do host planets, the number of planets that, basically at the right distance that are rocky planets, but, and so on. There's like 8 or 9 factors to this equation or whatever. And the interesting thing is, in the 70s, we knew how many sun-like stars there were in the galaxy. That was all we knew when this equation came out. And now it's kind of like, we know initially, even when I was studying as an undergraduate student, one of the factors is that the fraction of stars that contain planets. So that fraction, that number is going to be somewhere between 0 and 1. It's either going to be none do, or it's going to be 1. All of them do. And we're actually pretty sure now that it's 1. Like every star has planets around it. So that's one more thing we've been able to tick off the Drake equation. But the rest of the factors are kind of, how many habitable planets are there, or what fraction of these rather are habitable planets? And that's the stuff that we're trying to work out now. That's the stuff that we don't know.
All right. In a kind of similar vein, I suppose, Chromium52 asks, the impressive list of requirements in the rare earth hypothesis checklist, how independent are the probabilities? Could it be that they all line up more often than you would think?
So independent probabilities, they're not independent, right? I think in some way, shape or form. Well, some of them maybe are independent, but things like, for example, one of the things I didn't talk about was magnetic fields and the interplay between plate tectonics, for example. So plate tectonics, everything on Earth used to be Pangea, used to be one landmass. And the separation, we think, has helped to increase things like migration, biodiversity, and evolutionary competition, which has helped towards complex intelligent life, which is one of the factors that we need in order to broadcast. But one of the reasons that we have plate tectonics is because we have a thin lithosphere. If we have a thin lithosphere, basically able to float and kind of pull apart. If the lithosphere was very thick, that wouldn't have been the case. So, but that is obviously also related to the magnetic field. So in that case, the probabilities are not independent. For some of the stuff, the probabilities kind of are independent. And maybe it's the case that, okay, actually 100% of the time, in rocky planets, you could have a thin lithosphere. But maybe you don't always have a magnetic field, but that doesn't seem right either, you know. To me, I think some of them are independent, some of them are not. You know, it's quite clear to me that orbiting the right distance around the right kind of star, okay, those seem to be two independent probability distributions. But, you know, stable for geological timescales and complex life evolving, these are not independent probability distributions. They probably have shared variables.
Yeah. Okay. The next question has come from Steel Wolf again, Don, who asks, what technology or physics will we need to reinvent or completely break to explore the vast distances of space? And will it remotely resemble popular fiction?
Good question. So I think, you know, the ultimate question is, I think, speed of light travel, right? So fundamentally, everything we have ever been able to test about the theories of general relativity and special relativity have been true. Never ever been found to break the laws of physics in this way. And one of these is that, you know, the speed of light is an inertial quantity that is observed to be the same to all observers in all reference frames. Fundamentally, what it means is that the speed of light is always the same, and you can't change it, and you can't go any faster than it either. So if we wanted to be able to go and explore other galaxies, you know, we would have to find a way to preserve ourselves while we were getting there, right? You'd have to go into, you know, some sort of stasis and some sort of thing that could keep you alive for millions of years while you went to a different galaxy, for example, because the fastest that you could potentially travel is the speed of light. I think it may be possible to travel at the speed of light one day, you know, things like light sails, for example, to continually get up to that speed. Yeah, maybe that's possible. It doesn't change the fact that humans die after 80 years. So we'd have to find a way to preserve ourselves, or some people would have to volunteer to maintain a very boring civilization on a ship on the way over there. So I think it's more about the human cost, I think, in order to go and explore elsewhere. I don't know. I mean, the only other option, I guess, is that we come up with some sort of way to, you know, teleport or transport people. But I don't think that seems very likely, considering that, you know, general relativity must be obeyed.
Yeah, and even if we find a way to preserve humans or have some kind of generation ship, it's all well and good for the people on the ship, but those of us who stay on Earth will never find out if they made it.
Mm-hmm.
Okay. Steve asks, if the gas giants are eating all the rocky asteroids, are they full of rock as well as gas?
So that's a good question. And so I'm not a solar system scientist, but there's been an awful lot of research on like trying to get to the bottom of whether or not giant planets have like meaningful cores in any way. So cores, you know, kind of containing heavier elements, for example. And sorry, there's somebody playing really loud music right outside my window. Hopefully you can't hear it. So whether or not they're full of rock is kind of uncertain. But one of the things that we know is that certainly Saturn and Jupiter have certainly have some magnetic field. And that tells us that there must be some sort of conducting material inside, like iron or nickel or cobalt or something. One of these, probably more likely to be iron and nickel than it is to be cobalt. Just by virtue of the fact that there is a magnetic field present. I mean, they're certainly full of the rock that they eat. Whether or not they're full of like actual rock the way that we think of the surface of the Earth. We know these things kind of don't have surfaces, not in the meaningful way that we think of surfaces, because they are just gas giants. But it's a bit perplexing about why they have, you know, powerful magnetic fields if they don't have, you know, some heavier elements that are somewhere in between hydrogen and iron.
Is the amount of rock that they eat as asteroids just tiny compared to the size of these things? They're not.
Yeah, absolutely. So yeah, I mean, asteroids are pretty tiny compared to, you know, the mass of any of the planets, and Jupiter's pretty big. So yeah.
Why is it that the asteroid belt in our solar system is so near to the planets that you would expect to eat it?
So the asteroid belt basically exists because it's right on a gravitational resonance. And because it's on a gravitational resonance, basically what happens is you get these tidal forces that continually pull it apart. So if it wasn't for if it wasn't for the fact that it was in between two planets that are in this, and there being a gravitational resonance there, it probably would have formed another planet itself. But that's why it's there, basically. It just can't, it just continually gets pulled apart, because what happens is, if you have things in a resonance, what happens is you basically get this boost because they're meeting at the same position every time in their orbit. So it continually kind of pulls these apart and gives them a little jolt, which stops them from forming and coalescing into a more concrete object.
Okay, thanks for that. Thanks for indulging my question, but I just stuck in there. So the next question comes from Anonymous, which is, in multiple planet systems, the radial velocity of the parent star would presumably be quite complex. How do you find the individual planets from that data?
Yeah, so in that case, what you do is you basically signal fold. So you need to be, it's often easier with machine learning techniques and models than it is to try and do this kind of manually. But what happens in that case, in fact, it also is kind of true for transits, is you stare at the thing for a really long time and you fold the signals on top. And then what you do is you fit the data. So what you'll be able to find is, okay, a model with 6 or 7 planets is, a 99.99% fit to being present in this system. And you kind of do it that way. You basically continually fold the signal until you basically increase the signal to noise ratio. And then you find the best fit model to determine how many planets are present in that system.
I used to solve a lot of my problems when I was a scientist by staring at them for a really long time as well. So that completely checks out.
Sometimes crying and kicking things. Yeah, I'm not going to lie.
Okay. We've got a third question from Steelwolf on something of a roll. Given your statement about us being alone in the universe, what do you think of programs such as SETI, and is there a better method of searching?
So I think SETI is great. So just for anyone who doesn't know, the SETI program is a search for extraterrestrial intelligence. There's also this cool thing called SETI at home. So you can basically download this little program that just runs off your computer's CPU, and it basically scans for signals of life in the universe. It's pretty cool. I think it's good, and I think it's important. I'm very much, just to be clear, I think the search for extraterrestrial intelligence and the search for life elsewhere in the universe is really, really important. I think it's something we should continue, and I certainly hope that there's somebody out there. But what I hope and what I think are true don't always line up. So I think it's really important, and it's I've been in kind of involved on the fringe in a few ways for things like this. But yeah, I'm very interested in things, anything research wise to do with the cradle of life or anything like that as well. Yeah.
I think we're going to wrap up in a minute, so we're going to close out with one last question, which is, one of our organisers remembers that you have met Peter Higgs once or twice, and is there a story there?
Yes, there is. So I met Peter Higgs for the first time shortly after he'd won a Nobel Prize. And I was a PhD student in Edinburgh, and I was so excited to meet him. I was so excited. But I was a PhD student, I had no money, and there was free wine. So I was also kind of nervous because I really wanted to meet him. So I tanned like 3 or 4 glasses of wine. And anybody who knows me knows that I'm a lightweight and I have to be put to bed in disgrace after 2 beers anyway. So I was like 4 glasses of wine in. And then I saw my chance where he wasn't talking to anybody. So I make a beeline for him with a glass of red wine in my hand. Because I'm really clumsy, trip over my own feet and proceed to slosh him, myself, and this Swiss diplomat who was next to him in red wine. And I sort of landed and caught myself, held the wine really close and just went, fuck, and then left. And then the second time that I met him, I was like, this time I'm going to talk to Peter Higgs. So I met him in Marks and Spencer's. The poor guy was just, minding his own business, trying to get like a frozen microwave meal or whatever. And I was like, yeah, can I get a picture with you? And I was so excited. And I was like, yes, I'm going to get a picture of Peter Higgs. And I take my phone out to take a selfie. And because I was a PhD student, I didn't have any money. My phone was crap. And literally, as soon as I turned the camera on, it just died completely. And there was just a black screen. And I was like, I have waited for like 3 years since I first met him to take this picture. But I just was like really awkward. And this poor like 8-year-old guy was just like, yeah, okay. And so I just went, click, and just pretended that it took a picture and then ran away. Yeah, so I've met him twice. Both times I embarrassed myself, which was great. So,
but the second time he didn't know. So
the second time he didn't know that I'd embarrassed myself, so it was kind of fine.
Yeah, and I mean, anybody who's been to the QED mixer has at least come close to pouring wine over their idols. So
yes, I feel like that's a universal experience, embarrassing yourself at some point.
Yes, I think so. Okay, well, that's the end of our questions. So thank you so much for answering all of those. And thanks for giving us such a brilliant talk. We're not going to have a talk next week. We've moved to fortnightly now. So our next talk is going to be the Thursday after next, on the 19th of August. It's going to be all about QAnon, and it's going to be all about QAnon. We can't tell you that on Facebook in case they ban us from advertising conspiracy theories. So please spread the word as best you can. Other than that, a few of us are going to be meeting in the lock-ins razor afterwards. There's going to be links to that in the Twitch chat if you want to join us. So everybody's welcome. And that's all we have to say. So have a good evening, have a good week, and have a good 2 weeks. And we will see you next time. Goodbye.